what else could happen? Like you could get disconnected from the spaceship. Okay. All right, you may go. You're welcome. Bye-bye.
All right, we'll wait a minute or two for more people to log in. Got 6 students so far. Can you guys see my screen?
Yes.
Yep.
All right, go to Blackboard and download the file. Where is it? It's gonna be single thin lens diffraction limit. It's I posted it. What single thin lens? When is it diffraction limited? I posted it on April 6th. I think. Actually, this might not be that file. So you guys download that and I will open up the one that I actually posted. Why is it showing me this? I'll show, got it. All right. And we have still just 6 students. All right, we'll wait a few more minutes. Then hopefully you'll see something that looks like this when you open the file. Okay, wait one more minute, see who else we get. All right, so last time we talked about the modulation transfer function. And I said that its formal mathematical definition is that it is the Fourier transform of the point spread function, or the function that
Dr. Small,
yeah,
there's a question in the chat.
okay. What was why am I not seeing it? All right. Why is it not popping up? Come on.
I can ask it here if you want.
Okay.
In project 10, I forgot if we were supposed to use the FFT MTF or the Huygens one.
Huygens, and it shouldn't matter too much. Huygens is more accurate, but it can be a little more taxing on the processor. Whereas FFT stands for fast Fourier transform, and it is, well, fast. So either one. And why is the chat? Oh, Christ. Why is the chat not show? Okay, there. Now I'm putting it on my other monitor. Okay, and this is Orphan Black. It's a show about clones. So all of these characters are played by the same actress, and they're all clones of each other. But anyway, all right. Modulation transfer function is the Fourier transform of the point spread function. It's just the function that tells you how much light gets spread out. It also has a very, very intuitive definition beyond just saying mathematically it's a Fourier transform. You could think of it, and although they put the label MTF here, here they're calling it OTF, that's optical transfer function, and modulus is absolute value. It's important to use different words so that no one can actually tell what you're talking about. That way it's more impressive, I guess, if you keep changing your terminology as much as possible. So this is the Fourier transform of the point spread function. And let's see, we said that it's going to be roughly, if we were to look and ask where it cuts off, where it has decayed to about half, well, that's going to be at something that's proportional to 1 over the spot size. And if we're in the diffraction limited regime, how does the spot size depend on aperture?
It's proportional to it.
The spot
Linearly.
size is inversely proportional.
Oh,
So this should be proportional to it because it's inversely proportional to inversely proportional. So let's see what happens if we double the aperture size. If we double the aperture, then that cutoff frequency, now you could ask, well, should we do a quick focus? Yeah. And now it's at like 30, whereas before it was at something that I forgot to note the value of. It was at about 15. But as we keep increasing, we are going to find that now the cutoff, well, it's about 60. Let's go out to 16. And let me just make sure that, yeah, we're not in any danger of overfilling it. Now we notice that it's actually gone down again. As we keep increasing the aperture, all of a sudden, instead of continuing to get this cutoff at higher and higher frequencies, meaning that we're passing much more rapid oscillations with finer spatial details, now it's started to decrease. It's gone from 60 down to about 40. What's going on?
It's starting to become aberration limited.
Yes, it is starting to become aberration limited. And if we look at the point spread function, we can see that now, instead of having this nice, having all of the energy confined into the central peak, the secondary peak looks pretty bright as well. The energy is being spread out among multiple peaks, rather than being concentrated in the center. That's one of the signatures of something that's aberration limited. We could also look at the enclosed energy diagram, and we'll do it with the diffraction calculation. And we could see again that the enclosed energy no longer matches up with the ideal for the diffraction limit. And so what I basically want you to do for next week is verify that this behaves a lot like the spot size, that whereas you would find that the spot size was inversely proportional to aperture for small aperture sizes and proportional to aperture cubed for big ones, here we're going to get proportional to aperture and then proportional to 1 over aperture cubed. That will be a sign that all of this makes sense. Any questions so far?
Professor, I have a question.
Yeah.
So for project 10, we would have another field. And I believe there's going to be like 2 tangential and 2 sagittal. Which one should we look out for when we're looking at the Huygens MTF?
Right, so if we go off axis, first let's talk about what tangential and sagittal mean. I always get these mixed up and have to go over them, but basically, if we have an off-axis field, if we have something that's focused off axis, then you could ask, well, okay, well, what if instead of just projecting a point there, what if we projected some sinusoidal modulation there? So we project like a grading pattern on there. The modulation transfer function is a measure of the fidelity with which that grading pattern is reproduced. If it was, does it have the same contrast? Does the pattern we see projected by the lens have the same contrast as the input pattern on the left side of the lens? The thing is, if I project a grading pattern onto there, well, I could oscillate it horizontally or vertically or diagonally or anywhere in between. And one of those directions is called tangential, and one of them is called sagittal. And I always have to look it up. I believe the tangential is the direction from the optic axis to the off-axis field, and sagittal is perpendicular to that. But for these purposes, what I would probably do is either use the average, the midpoint between these two. You see that for this off-axis field, the tangential is here and the sagittal is there. Either look halfway between them or just take the worst one, because really it's the worst. You should probably take the worst one because it's the worst one that limits your performance in general. You know, this is one of those things where the chain is only as strong as its weakest link. Other questions?
Professor, so it's the worst one of the object that is off axis, right? Not the
Yeah.
Okay.
So we're comparing, what depends if you want to look at on-axis performance or off-axis performance. And the fact that it's wider, that it goes out farther, sometimes people think, oh, that must be a really good thing. I mean, look, the on-axis is actually going out to a smaller spatial frequency than the off-axis. So you might think, oh, wow, we can get sharper images with off-axis. Well, here's the thing. If we look at a spot diagram, or actually let's first look at the PSF. I don't even know if the PSF will plot. It's going to be, let's look at field. Why is it not letting me look at the other field. Let's just look at a spot diagram. What you should see is that it's sharply elliptical, right? Because of coma and astigmatism. And because it's kind of sharply elliptical, there's actually tighter focusing in one direction than the other. And so because it's tighter in one direction, that manifests as a smaller spot size. And because it's smaller in this direction than in this direction. And so if it is smaller in this direction, well, spatial frequencies are inversely proportional to spot size. So that means that it's not going to spread out. If I modulate something horizontally, I got a bunch of vertical stripes, which you might think, wasn't that a vertical pattern? Yeah, but they're spaced horizontally. And so because they're spaced horizontally, what will limit how well we can see this is how much it blurs horizontally. We don't get as much horizontal blurring as vertical blurring. So we should be able to transmit better space. We should be able to transmit higher spatial frequencies in the horizontal direction than in the vertical direction. And if we go to the MTF, we see that indeed, in one direction, we're able to pass higher spatial frequencies. And that direction is what they're calling sagittal, which is, in fact, if we look at the spot diagram, the horizontal direction. So what I said before, this is how I figure it out. I either look it up in a dictionary, well, not literally a dictionary anymore, but I Google it. And then you have to, the definitions don't generally say something very straightforward. They start saying in a direction that is perpendicular to something that involves whatever vector or yada, yada. And then I have to puzzle through that. Or I just go to the spot diagram and say, okay, is it narrower horizontally? Because if it's narrower horizontally, if it's narrower horizontally, then it must be transmitting higher spatial frequencies horizontally. If it's wider vertically, it must be passing lower spatial frequencies vertically. And that's how I think about it. Any questions? Going once, going twice. Why is this stupid thing? Now I want to see what would happen if I put field 1 off axis, I mean. Now what would it look like? Okay, and indeed, we see something that is narrower in the X direction than in the Y direction. It's qualitatively similar to the spot diagram. It's not exactly similar. It's not exactly the same as the spot diagram, but we wouldn't expect it to be because the spot diagram is based off of different physical assumptions than the point spread function. The spot diagram is not taking into account wave optics, but in the aberration limited regime, where interference effects are not really what limits the spot size, we would expect that they would be roughly similar. Anyone else? Gotta be honest, I just like playing with simulations. That is, for me, one of the more fun things in physics, is to just sit and play with a simulation and see that a calculation done very precisely by a computer matches up with everything qualitatively that I knew. To see that my qualitative understanding can match up with a high precision calculation is just plain fun. It's one of the things I love most in physics. I've often told people that spring semester is my better semester because no matter how much things stress me out, every week at some point, I'm going to get to play with Zmax, and then I'm in my happy place. Okay. Nothing else? Then let's talk about this paper that I posted. All right. Paper that I posted is on tube lenses and beam steering lenses. And so we need to talk about what those are. Actually, I think I'll go back again to my other device and let's look at the paper initially. Scan and tube lenses. So as you can see, the authors of this paper are in a neurophysiology and neuroscience lab. And this should not be a terrible surprise because there are a lot of physicists in neuroscience for the simple reason that in order to understand neurons, you wind up doing a whole lot of electrical experiments. And so a lot of the people working in neuroscience, they might have been biology majors, but they were biology majors who did well in physics and math. Some of them started off as chemistry majors. I know at least one very good neuroscientist in our biology department who started off as a chemistry major and then did his PhD in physiology doing highly quantitative experiments. Some of them come from physics because, again, there's a lot of math, there's a lot of imaging, there's a lot of electrical measurements. And what they're talking about is laser scanning microscopy, which we'll say more about at the end of the semester. But here's the basic idea. You have a scan mirror, okay? You're collecting information one point at a time. You're just scanning through the specimen, literally looking at one point at a time. And if we zoom in on this diagram, you will see that these three colors are focused at different points in the specimen. And that's because through this long chain of mirrors, they came in initially at different angles. The reason why we collect information point by point is in these kinds of experiments, they shine usually a very intense beam of light. And that intense beam of light gets focused to a point, and they take advantage of something called a nonlinear effect, which means that you basically get no light from anywhere unless the beam that was focused there is really, really intense. Now you might say, well, isn't that true of all light processes? If something's going to glow, I shine a faint light on it, I get a faint glow. I shine a bright light on it, I get a bright glow. But this is nonlinear, which means that if you double the brightness of the beam you're shining on, instead of getting something out that's twice as bright, depending on the type of experiment you're doing, you either get something out that's 4 times as bright, or 8 times as bright, meaning 2 squared or 2 cubed. You get something out that's proportional to either the square of the input or the cube of the input, depending on what you do. And what that means is that they're often trying to image inside of a brain. Now, brains aren't perfectly transparent, to put it mildly. Brains are rather translucent. So there's going to be a whole lot of scattering and spurious signal. And if you just focus, if you use a technique where you're really only getting your strongest signal, where you're getting a disproportionately strong signal from a place where the light is strongest, then you won't have to worry much about light from anywhere else. Any questions on that idea? Okay. So there's a long chain of lenses here. First, we have the scan lens. And what the scan lens does is, well, it takes light coming in whatever angle, angle theta, and it focuses it a distance in its focal plane, a distance f tan theta from the axis. Nothing too profound yet. But what that means is that we have a point here that is very far off axis. And then it sends it through two more lenses, a tube lens and an objective lens. And don't worry for now about the focused spots here. The important thing to realize is that we are essentially demagnifying. The microscope magnifies, well, we are demagnifying because instead of taking light out of the microscope, light coming out is magnified, we are demagnifying, we're sending light in. So if we focus it really far off axis here, it will get focused really close to the axis on the other side. And indeed, they're really close to each other over here and really far from each other over here. Any questions on that idea so far? We'll talk more about the tube lens and the objective lens in a bit, but let's just take it as a given for now that this pair of lenses is able to focus the light to wherever we want. And if we just tilt this mirror to a different angle, we could change how close to the axis or far from the axis it is. And we could thereby change how close or far from the center the light focuses over here. Okay, so that's how we can do point by point. Now, the light that comes out, we send in light at one wavelength, it glows at a different wavelength. And we've got what's called a dichroic mirror here. It's a very unfortunate name because if you search for the word dichroic, dichroism refers to something that that has to do with polarization. And this isn't about polarization. This is a mirror that reflects some wavelengths and transmits other wavelengths. So it's basically a wavelength selective beam splitter. You're probably wondering, how do you make something that transmits some wavelengths and reflects other wavelengths? The answer to that is going to be discussed next week when we talk about how to design thin films and make filters out of thin films. And that's why we're going to be using Python. Now you might be thinking, okay, well, all this light comes out and the light that comes back out comes through the objective lens, hits this, gets reflected. Don't we need to focus it? The answer is actually not that much. And that may seem weird to say, but because we're going point by point, we know that any light that comes back must be from whatever point we focused it on, because everything's nonlinear. And if it must be from whatever point we focused it on, then we could just assume, we could just send it all to one detector. We could just have one big surface somewhere out there. This mirror is pointed at. And we know that any photon that hits that must have come from the point where we were focusing. And any photon that hits that and produces an electrical signal, all of that gets added up. And we say, okay, that's how much light came from this point. Then we do it again and we say, all right, that's how much light came from that point. And then we focus again and we say, that's how much light came from that point, and so on, and so on, and so on. Any questions so far? You know what, let me skip ahead and just tell you why people do this. Let's going to talk about this later in the semester, but the more I think about it, basically these techniques are used for looking deep into mouse brains. And why mouse brains? Well, because they can look a few millimeters in the best cases, looking a couple millimeters into a human brain isn't going to tell you much. I mean, there are humans with brains that are just a couple of millimeters in size, and we're very happy for them that they got a job in Congress. But, you know, most human brains are much more than a couple millimeters. On the other hand, looking a couple millimeters into a mouse brain, well, that's a sizable fraction of the distance into the brain. You're looking at a pretty sizable portion of the mouse's brain. And somewhere in here is a figure. He's showing, this is by Chris Hsu, a guy who was at, who started his career at Bell Labs and then was working on pulsed lasers for telecommunications, and then went into using pulsed lasers for doing brain imaging. So if you can go a couple of millimeters, here we're down to 1.2 millimeters, into a mouse brain with one of these multiphoton techniques, you can see several different layers. You can see the neocortex, the white matter, and the hippocampus. So you can see distinct regions of the mouse brain. And since this article was published, people have only improved their ability to do these things and to collect different types of data simultaneously, to simultaneously get structural information on the brain, and to use voltage-dependent dyes, which can measure electrical activity, and to use, and to also potentially do direct electrical measurements on the brain, and to even do these things on a mouse that is moving. Basically, they cut a little hole in the skull and they anesthetize around that hole so that the mouse doesn't feel any pain. It doesn't know that its head is open. And they clamp something onto the head that is doing all of this imaging. And the mouse is allowed to run around in its cage. And that means that you're watching brain function in a mammal that is conscious and using its muscles and using its mind and looking at things and processing information. And I don't know the latest status of what innovations have come from that, what innovations in the understanding of neuroscience have come from that. But I know that that's got to be way better than looking at a mouse that is under general anesthesia and sleeping. A mouse that's only under local anesthesia and running around and looking at things and using its muscles and engaging in, well, it wouldn't be hand-eye coordination, foot-eye coordination to navigate its environment, that could potentially tell you things about how mammals use sensory information to control their muscles. That could tell you things that actually matter for human disease. You could give that mouse alcohol and see what happens when it's drunk and learn things about substance abuse and how it affects humans. You could give that mouse, there are mice that have, or as far as we can tell, seem to have diseases analogous to human mental illness. You could watch a mentally ill mouse walk around its cage, engaging in activity, and see what is happening in different layers of the brain. And that is a tremendous thing to know what is happening in the brain of a mammal with mental illness while it's engaging in some semblance of normal activity. I think it's pretty obvious why we would like to know that. So that's why this stuff matters. And there are a lot of physicists who work on this because obviously you need a tremendous amount of biology knowledge in order to handle the mice, to know what you should be looking at in the first place in the mice, in order to keep the mice alive in these experiments. You need a ton of biology knowledge. You also need a ton of optical engineering expertise to build these things. And one of the key issues is delivering very high power light pulses. We'll talk more about that later in the semester, but delivering the high powered light pulses over a very short interval of time is important. That requires very good laser development and very good fiber optic development. And so Chris Hsu is a physicist who started his career at Bell Labs working on telecommunications, but all of the things that were used in telecommunications can also be used for this. Any questions so far? Somebody must have a question. I just told you how people are building things to look in, are using optics to look inside the brain of a mentally ill mouse and hopefully someday come up with cures for human disease. Someone's got to have a question. Come on.
Professor, I have a question. I was just wondering, why would we use, like, I guess this type of technology when we have like radiology imaging? Like, yeah.
Okay, so a couple of reasons. First of all, yes, they can do brain scans on humans. An MRI is primarily looking at density. And you can learn a lot from that, but there are limits. It's looking at density and it can look at blood oxygenation. So a functional MRI is basically looking at blood flow in the brain. You can put a human inside of an MRI, but a human in this very confined space. I've had MRIs on 2 different occasions, one for some neck and jaw issues and one for issues in the hand. And even when they worked on my hand, I still had to, my hand had to be in the center of the machine, which means that my head had to be at least partway in there. There is nothing natural about this environment, okay? So a radiologist can look at a human brain and see things, but that's entirely different from looking at an animal running around. Now, they do functional MRIs where they put humans in these machines and ask them to engage in certain cognitive tasks. And then it lights up and you say, hey, all right, so this part of the brain got more blood flow. Something's going on in that part of the brain. And then you say, hey, now do this math problem, and something lights up. And then you say, hey, tell me something you remember from 1st grade. Oh, okay, accessing old memories lights up that thing. Now I want you to think about, I don't know, a happy relationship. Ooh, emotion lights up that part of the brain. They learn things from that. But again, they're only able to look at certain things. Looking with optics gives you a whole lot more chemical specificity than you can get with most of the things that a radiologist can look at. And it gives you this chemical specificity while looking at a mammal running around in its native environment, not native, sorry, running around engaging in activities that make use of its muscles. And there's a bunch of things that can be said against using mice for research. The short argument against using mice in research is that doctors have cured cancer in mice thousands of times. Open up any science journal on any day, and you can see a report of something that cured cancer in mice. And yet somehow humans continue to die of cancer. So mice aren't exactly like humans, but they're placental mammals. They're even more closely related to us than a lot of other placental mammals. They're closer to us than, I don't know, dogs or horses are. I mean, they're not the worst model organism out there. And they're a model organism where a millimeter gets you a large fraction of the brain instead of a small fraction of the brain. So that's why they do that. Other questions?
Professor, there's a question in the chat.
Okay, for some reason the chat keeps not showing up for me. Where did the chat box go to? What's the mouse utopia experiment? I'm not familiar with that. Anybody tell me what the mouse utopia experiment is? Meanwhile, I'm going to look for video of that. There have been videos of mice running around in cages with these things attached to their heads. And for some reason, it doesn't want to scroll down. So they have shrunk these things down considerably. Now, this is just controlling, this is just wired to one very specific site. But let's see. I have seen videos of these tiny head-mounted Mark Schnitzer. Okay, so Mark Schnitzer is a biologist and neuroscientist at Stanford. And I knew someone in his group who was working on a very different type of optical imaging, but it makes sense that he'd be working on multiple types of these things. So they've basically got a thing wired to the mouse's head. They have to have it on top of the head so they could send the fiber optic cables. And they are on the left, you see video of the mouse running around its cage. And on the right, you see neurons firing. And you see fluorescence from that. These are calcium dependent dyes. So they're monitoring calcium ion activity. Okay. Scan brain activity in something like the mouse utopia experiment. I am not familiar with that. Now I'm looking back at the chat. A giant cage, and they're given food, water, nesting materials. So it sounds like in a much more enriched environment than they normally get. I have heard that mice, it's probably better to study mice in more enriched environments, not just for humane reasons, but if we want to understand disease in a human, I mean, okay, yes, lots of humans experience distress, but still not everybody is undergoing the same level of agony as a mouse in a lousy lab environment with very little freedom. So a mouse that's under somewhat less stress than that might in some cases be a better model for human brain activity. I'm not sure if they're there yet because that sounds pretty big. And at the moment, these things are still done with cables running into their head. And so if the mouse started crawling through tunnels, you'd need to have one hell of a long fiber optic cable. I don't think we're there yet, but if there's one thing, as time went on, the mice made gangs, harems, and other human behavior. I wouldn't call it human behavior. I'd call it social mammal behavior. To think that we are somehow that different from other mammals. We have most of the same genes as other mammals. We use them differently, but hell, there are genes in mushrooms and fungus that show up in humans. Because at the end of the day, we're all eukaryotes. All right, so that's why. Any other questions on the why of this? Then let me give you one other story. Nonlinear microscopy, all right? I told you that this relies on nonlinear effects. Well, nonlinear microscopy, the theory of nonlinear light emission multiphoton light emission is what I should really say for various reasons. The theory of multiphoton light emission goes back to Maria Geppert-Meyer, who to most physicists is probably more famous for her work on nuclei, and she won the Nobel Prize for that. But in her PhD thesis, she worked on multiphoton emission of light. Now, at the time, people didn't have lasers, and you need the type of intensity and focus that you can get from a laser in order to test these theories. This was done in the 30s, so at the time, it was purely theoretical. Come the early 1960s, people have lasers. They're able to test the theory. Not surprisingly, her theory was correct. Then they spend a couple decades making advances in lasers and fiber optics. Finally, in the late 80s, they were able to start applying these kinds of techniques to microscopy. But it took, in the real place where this came from, and all the real innovation there happened not in biophotonics, biomedical optics, but it happened at places like Bell Labs for the telecommunications industry. Then people started working on applying this stuff to biology. And it still took another couple decades before this kind of imaging went from something that a few specialists could do to something that's almost a routine, that basically is at this point a routine instrument in a neuroscience lab. And I say this because the progress of science is very, very indirect and winding. It starts with Maria Geppert-Meyer just doing very basic theoretical quantum physics during her PhD. Then it goes to experimental optics 20 years later, a little more than 20 years. Then it goes to engineering and telecommunications for a few decades. Then it goes to some very specialized biophysicists. Then it becomes a standard tool used by all is a strong word because there are many specialties, used by a great many neuroscientists in the 2010s and 2020s. And so we really cannot predict what will matter in what areas down the road. It's worth noting that in the stuff that I've done on biomedical applications of optics, I've cited papers from a lot more than just biomedical optics people. I've cited papers from people working in virtually every branch of optics. I've cited papers on algorithms developed for data analysis and astronomy, algorithms developed for cell phones. You really can't predict which direction these things will go in. Any questions on that history? Okay, so then we're back to these lenses. So what we want to try to understand in the next hour is what are the scan and tube lenses for, and why, what did this guy do to improve them? There's really no other questions about looking inside a mouse brain. I gotta be honest with you, my family gets a group rate at the neurologist and psychiatrist. So I just find it endlessly hopeful to know that there are optical engineers working on ways of looking inside the brain of a free-moving placental mammal that isn't that distantly related to us, because believe me, we need that. Okay, so microscopes. The idea of a microscope in principle would seem quite simple. We've got an object that is almost just a little more than one focal length away from the lens. And if it's just a little more than the focal length away, it produces an image very far away. That's the idea. And it would be that simple if we didn't have aberrations and we didn't have scattering. S1 is roughly F. S2 is much larger than F. Now, what people do oftentimes, at least in some microscopes, is that they make what they call an infinity corrected objective. Infinity corrected lenses aren't always the best choice, but in some cases they can be a very good choice. So what they do is they have a lens that will take light from a point and it will just send that light to infinity. So this is exactly one focal length away. If it starts at distance y off axis, then tan theta is y over f. And I should really call this FO for the objective. All right, this is an infinity corrected objective. We can't make an image out of that exactly, but we then just put one other lens. We have our tube lens, and the tube lens will take these rays and it will focus them one focal length away. Oops. So I should really be calling this Y1. Tan theta is Y1 over F objective. And this would be Y2. And Y2 would be FT for the tube lens. Y2 would be F tube tan theta, which is F tube times Y1 over FO for the objective. Any questions on that idea? So in principle, as long as we have a tube lens with a really long focal length, we could ideally have a freaking huge, 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 huge magnification. People generally don't do magnifications. You rarely see a magnification on a microscope much above 100 or 150. And you might think, well, why not just make the magnification even larger? Why not make the magnification 1,000? And then surely we could see, instead of 100, we go to 1,000, we could see things that are 10 times smaller. Do you think that's true, that we could see things that are 10 times smaller?
Well, then we run into limits, like the diffraction limit.
Yep. In this case, the way I've set this up, we're only getting light from a portion of the lens. And so we would want to figure out, I'll call this angle, instead of theta, I'll call it alpha, just to keep it distinct from the theta over here. All right, so the spot size over here should be 0.6 lambda over n sine alpha, where n is probably 1, but I don't know, if for some reason you focused it in glass through glass or something, it could be smaller. But the point is that it's going to be 0.6 lambda over the sine of this angle. And this angle is probably substantially less than 90 degrees. And so you're still going to run into the diffraction limit. People have found through practical experience that 100x magnification is usually good enough. Once you're at 100x magnification, what's limiting you is diffraction at that point. So you don't tend to make it any larger. But in principle, somebody could, if they wanted, just put in a tube lens with whatever focal length. And God knows it's not difficult to make something with a long focal length. To make a long focal length, you make a surface that's less cubed. And we've said a lot of things about how aberrations are more of a problem when you have a surface that's highly curved. But if it's less curved, well, that's easy. If it's less curved, you don't have to worry. Okay, so now that's the role of the tube lens. We've also got the scan lens. So the way these things work in general is we've got our beam splitter. And we've got our objective. And then we've got our tube lens. And we've got, I'm going to do a simplified version of things. Oops, that should not be. We've got our scan mirror. And so we send in laser light to the scan mirror. And then whatever angle it hits this at, and I should really draw it wider so that we can send more light onto it. All right, whatever angle it hits this at, that will determine, we'll call this theta. It will get focused over here, a distance y off blah. If I send it in, we need two lenses. I can make room for a second lens because I never labeled the first lens. So we'll call this lens the scan, and we'll call this lens the tube, and none of this, what I'm about to do, is to scale. So it goes here and y1. All right, so all of these things are coming through. They all get focused to, they all get focused to a point. They go through this at an angle. This is theta 1. They get focused at y1. They make an angle theta 2 coming out of the tube lens. And then finally, they get focused here, a distance y2 off axis. So y1 is equal to F scan tan theta 1. It's also equal to F tube tan theta 2. Any questions on that idea? And then finally, Y2 is F objective tan theta 2. So tan theta 2 is equal to Y2 over F objective. So Y1 is equal to F tube Y2 over F objective, which we already know, which is also equal to F scan tan theta 1. So again, we're going through several conversions here. We decide what angle we're going to send the light at. And that angle is controlled by tilting this mirror. And tilting this mirror is really easy. There are materials called piezoelectrics. Can anyone tell me what a piezoelectric material is? Has anybody heard of piezos? Materials that make electric fields when compressed. Yes, but they also do the opposite. They compress or expand when you apply an electric field to them, depending on the direction of the field and everything. So voltages are easy to control rapidly. Electronics are fast. Mechanics is slow. So you apply a voltage to these materials and they will rapidly expand or contract. And their expansion or contraction will push or pull on a mirror. So you tilt a mirror. That sets theta 1. As soon as you set theta 1, the scan lens will give you a Y1. We'll focus the light at a distance Y1 off axis. Then the combination of the tube and the objective will take that light that was focused to a point Y1 off axis in this plane and move it to a point Y2 off axis in your object plane. And so we're left with tan theta 1 equals Y2. This is your target. You're saying, all right, I want to focus my light. Oops. I want to focus my light at Y2. And someone says, okay, we're going to have to send in a light at an angle given by tan theta 1 equals F tube over F objective F scan. So you program a computer to control all of this by saying, we're going to try the following Y2 values. We're going to first focus the light here and collect